Good afternoon, all of you. My screen is visible?
Visible, sir.
Yeah. Okay, we'll see today constant current versus constant voltage control. Here, normally the rectifier's side will be the constant current and the inverter side constant voltage. That is only the actual strategy. Anyhow, that will come later at classes also. And you can see that two obvious alternative ways of operating DC transmission system. Control of the transmitted power at each follows. We will see that one is the uh, current held at constant. That means we can able to operate. One thing is keep the current constant and voltage variation, and vice versa. Voltage, second one is a voltage constant and then current varies. So these are the two strategies in that HVDC transmission. You can keep that current constant and you vary the voltage. That way also you can possible. Otherwise, voltage make it constant and you can change the current. Same two methods could be used for even AC transmission systems also. Whether it is a DC or an AC transmission, that will be possible. Constant current system, various loads and one or more power sources are connected in series. We can notice one thing, if you are operating as a current system, that is a constant current system, the loads are connected in series. Similarly, whereas in the other version, the loads are connected in parallel. That is only the thing. You can see that a load or source is turned off by bypassing it after being voltage is to be zero. It is a only one voltage source if it having, it will be bypassed that. This method has been widely used in the street light circuits and all, because these are connected in series. Then the load source is turned off by bypassing its after being voltage is zero, and this will be used in the street light circuits and all. And the olden days, several HVDC transmission projects also they used this strategy. That means current constant, voltage varies. And other version you can see here, constant voltage system. The various loads and sources are connected in parallel. So that is only the different here. If it is a current source, you can keep it in a series. If it is a voltage source, you can keep it in a parallel. A load or a source is taken out of service by opening the respective branch. Suppose you want to remove the load, so automatically, because these are in parallel, anyone will be the open. So the particular load branch, if it opens, automatically the load will be disconnected. This system is in the general use in a AC transmission generally, and distribution also. We can use that also. In HVDC transmission system, having only two terminals. Only one is a positive terminal, another one is a negative terminal. So that leads what will happen. Whereas in the other case, in AC transmission, you may have ABC parameters, neutral wire, all these things. But in a DC transmission, we have only two terminals. Even in some cases, it is only the one terminal. There is a series and parallel connection of the two converters is disappears. So we don't bother about what is the inside of series and parallel connections, all these things, and finally we will get it. You can do the control strategy, all these things, but you will get only the two terminals in out. That is a common voltage and common current we need to operate. That is operating point. All that things will come under even the later slides. There is a characteristics. So what will happen if you are operating as a constant current and constant voltage in inverter side and the rectifier side? If anything voltage is increasing or decreasing in the AC side or DC side, or in the rectifier side and the inverter side, what is the operating modes? Normally here the two control strategy, if you speak broadly, there is a grid control, another one is a tap changing control. So tap changing control is very slow rate of control strategy. But whereas if you are operating under something like grid control, it is a fast control. So that that will come under next slides. So choice between constant current and constant voltage must be made on the other grounds based on the parameters. Also, we can able to see that on the difference. So concern as follows. You can see that first one is limitation of variation of current caused by the variation of alternating voltage or by faults on the DC line or in the converters. So there is a limitation of variations of the current. So when you are operating this constant current source or normal control strategy, this leads to what will happen, the variation of the alternating voltage. If you are make it as a variation of the current caused to the alternating, means AC side voltage is going to be fluctuate by faults on the DC line on the converter. So the fault may be occur in the converter side or maybe in the line DC line side. And the energy loss and efficiency, these are the differences concerned as follows. We need to consider these two things. And you can see it is well known that short circuit currents on a constant voltage AC system can be very great, limited by the system impedance. So normally when the system impedance is there, or preferably it is a reactant side, if any short circuit is occurred, so that will limit the fault current. And for that is the impact in that case limited by the system impedance. So that will be the take care of the AC system side. If any short circuit is occurred, then to avoid the higher currents, that will limited by the impedance, preferably in the major role is in the reactance. Constant voltage in the DC system, fault current could be conveniently be much greater, being limited by any circuit resistance, that is RC1, RC2 are there, no? That will be limited. Whereas in the AC side, that will be the limited by the system impedance, but whereas in the DC side, that will be limited by the resistance, that is a circuit resistance. On a constant current system, however, short circuit currents are ideally limited to the value of the load current. So it should not be beyond very high current. It will be value of the up to the load current in a particular practice to about twice the rated current. So that load current, you can able to happen any short circuit, that current will be rises high, but that current should not be beyond the twice of the rated current. So up to that it can withstand. Accidental open circuit could be give rise the high voltages. Why it will happen? If unfortunately if any open circuit is occurred, then voltage will rise. That is only the thing in the load side. Suddenly there, why the tap changing concept is even normal our distribution side also. The problem with I mean normal case, if any what you call it as loads are suddenly released or suddenly rise, then what will happen? If loads are suddenly released, then voltage will be high, means the voltage will rise. But suddenly, other case, if sudden load is increased in the load side, then voltage will be dropped down. So in this sequence, because the load is not a constant one, it is going to be vary whether in the any time with the distribution side or in the general case if you consider transmission also. So what will happen? Load is fluctuating. According to the load scenario, the dispatch centers, there is a normal local dispatch centers or central dispatch centers, all these things, they will monitor that load scheduling, and they will adjust that voltage taps, that is a tap changing transformer, such a way that you maintain as a constant voltage. Some cases if the feeder is very long distances, even distribution side also, at the end side, maybe in the last consumer may get as a less drop, because he, what they will do is a lot of non-linear loads are present in the previous taps. In that case voltage will be dropped down, then the tap changers will adjust the maintain as a constant voltage level. That's the thing will happen if unfortunately what will happen, the open circuit will takes place, then the voltage will be rises. But practically open circuit fault will occur rarely when we compare to the short circuit conditions. If anything is accidentally open, then voltage will be rises and you need to act accordingly. In a constant voltage system, the I square R losses in a conductor is proportional to the square of the power transmitted. So that is it, because our losses I square R in a conductor, because when the constant voltage is there, you are transmitting the power in the line. Obviously, you need to make use of current scenario there. Then I square R loss will be come into the picture, so that will loss will be the square of the power transmitted. Because it is a very sensitive parameter, the factor of current is I square, so that is the reason square of the power transmitted. In a constant current system, this loss is always as its full load value. In a constant current means automatically whatever the rated current is there, full load, so you can operate that in. But whereas in the constant voltage system, that current will be varies, that is the reason you will get it as a loss I square R loss in the picture. If the system transmits less than the rated power, because if transmission line, that we call it as a thermal limits and all, each line may have as a MVA rating, that is a thermal limit of a transmission line. If the transmits less than the rated power, in some cases, because if you are transmitting normally rated power has to transmit up to the thermal limit, and if you are unable to transmit that, and if you are trying to transmit the power less than the rated power, in as it is true in the nearly all the transmission system, because maximum limit is a thermal limit, always your transmitted power will be less than that of the thermal limit. If the transmitted power is more than the thermal limit, automatically there is a line outage is going to takes place. So if the line outage is happened, automatically whatever the load is there, that will be constant at that particular instant, but unfortunately one of the line is outage, the power has to be transmitted through that line will be zero, and we need to divert that power to other lines, then obviously other lines is going to be overloaded. If other lines are overloaded, then consequently other lines also will be occurred in the fault, and it may be leads to the overload on that particular line, and then consequences lines will be outages. That leads as a tripping. That is the reason normally when you are transmitting power, that is a load flows and all, when you are any fiber system or something, if you perform the load flow, you can able to observe that what is the line, what is the power is transmitted to the line 1 to 2 or 2 to 3 and so on. We can notice that comparatively with the thermal limits, all the lines power transmission through the particular line will be always less than the thermal limit. And some scenario, if you want to increase that power some extent, then what we will do is we can able to use the some control strategy. Let it be any of the line is less distance or less cost to transmit that, then what you will do is they use as a control strategies like resistance or impedance offered by that line will be minimized, so that you can able to transmit further power, but all that will be less than that thermal limit only. It should not be. When you are performing the load flow, we can notice that which line is having less power, and in that line, that is one of the option, not only all the cases. You just use as a series compensators in that particular line, then you reduce the impedance of that line, and so that it allow more power to transmit that particular line, so that if the line impedance offered by that line will be less, then automatically losses in that particular line also going to be minimized. That way we are able to reschedule that power. That is the optimal power flow. Whatever we had in power system and all, we are studying in that load flows, but later subjects will get it as a optimal power flow. In that case, rescheduling of the power to minimize your cost and then losses, all these things. So that is the reason here. The always the power transmission is less than the thermal limit only. Then otherwise also the true for the losses dependent on the voltage, such as corona losses and losses in insulation leakage, all these things also will be the problem. So in practice hour, the voltage dependent losses are always much less than the current dependent loss. That is always true, because voltage losses are very negligible amount, but only the thing is current dependent losses are I square R losses will be there. That is the more factor in this. Consideration of the losses favors the constant voltage system, but the limitation of the current favors the constant current system. So this is the loss favors the constant voltage system, but the limitation of the current favors the constant current system. And in the past, there was some uncertainty as the choice with the earlier DC project using the constant current. Some of the project they used that is already reported in the previous slide. However, it is possible by the use of automatic control to combine the best feature of the each. So it should not be as in one way. You just coordinate with this constant current and constant voltage, and you can able to bring out that operating point. You can move that one of the parameter by keeping one parameter is constant like that. We can able to possible to automatic system for the best performance. And instead of that way, you can able to mention like this also, constant voltage and constant current. So here in this case, first one is a voltage is constant, because we are operating as a constant voltage representation, and this is a current side. Current will be the constant. Current is varied to change the power, because the power is let it be both scenario, power is constant, and one we keep the constant, other one must be variable one. So to maintain the changes in the power scenario, you want to increase the power or decrease the power, P is equal to VI concept, one parameter is fixed one, so to change the P, automatically other parameter has to be changed. Similarly, in the constant current side, voltage is varied, because current is already fixed. To change the power, we need to vary only the voltage. Loads and power sources are connected in parallel in order to turn off the load or a source respective branches. But whereas here, loads and power sources are connected in series. That's what I mentioned in the first point itself. In a current source, these loads are connected in series. Voltage source, these loads are constant voltage. You can connect it in a parallel. So that's what mentioned here. This will be used in the street light in a DC side, and AC transmission and DC transmission will be used in the constant voltage. And DC system, the fault current can be greater limited by the circuit resistance. So in a DC system, we used as a controller 1, controller 2, that is a circuit resistance RC1 and RC2, that will be controlled. But whereas here, in the constant current side, short circuit current is ideally limited by the load current, and it is twice the rated current, and accidental open circuit give rise to the huge voltage. So these points are already covered in the previous. Only thing is, if the question asks to compare the constant current versus constant voltage, then you can make use of this table. And power loss is proportional to the square of the power transmission. Here power loss is directly proportional to the full load value. So, and then next topic is the desired features of a control. So what are the desired feature when you are designing as a control? We can take care of the some of the parameters. So otherwise the voltage may be rise, or current may be rise, or faults may be occur. So the control must be rapid, otherwise the fault clearing time will be more, that leads as a system problem. So that things we need to briefly I just listed some of the features. You can see that one is the limitation of a maximum current so as to avoid damage of walls. This is one of the factor we need to consider. So current should not be very high. There is a control is essential, as well as the current in that line, because we are operating, let assume that constant voltage operation, but current is need to vary to transmit the power, but you are keep on varying the current to meet your power demand, then what will happen, that current cannot be withstand by the walls, then all automatically walls may be damaged. That's why what you will do is maximum current to avoid the damage to the walls and other current carrying devices, because in a system not only walls, it may be some protective devices also will be there, like in normal forget about HVDC, in general any equipment in a power electronics controller equipment and all, whether it is a rectifier or inverter or a chopper, anything, if device is there in a circuit, main switch is there, but in addition to the lot of components also involved in it. Some cases when the device is conducting, let it be main thyristor is on, other devices also has to peer across the reverse voltages, peak inverse voltage need to consider, or even if device is off state, that current has to be bypassed through the auxiliary device or diodes, that has to take care of the components also. If we are increasing the maximum current, automatically one thing is main wall, other current carrying devices also will affect, so that has to be a limit, that is one of the limitation. And limitation of a fluctuation of current due to fluctuation of AC voltage. So obviously when the AC voltage is fluctuate, automatically the current also going to be fluctuate. So these are the, just I'm listing the some of the parameters and keeping the power factor as high as possible. So there is a major role in that power factor. Whatever you want to do, but that is will happen under control strategy. Some cases if you reduce the beta or increasing the beta in the inverter side, that will affect as the power factor also. Anyhow, that we'll see what is the advantage of keeping power factor is high. Automatically when power factor is high, losses will be minimized, because our case and it will transmit more power also if power factor is high. So like that, and if, what will happen if not, that also we'll see that point. So this is the major important point, keeping the power factor as high as possible. While you are controlling that inverter station and the rectifier station, you must keep that power factor as much as possible is high. And the prevention of commutation failure of the inverter. So if what will happen if commutation failure takes place? What is the meaning of commutation? Commutation is nothing but the process of turn off the device. At what instant the device is going to be turn off, that point we need to identify. And particular instant device has to be off. If suppose the devices are 1 and 2 is operating, and next device has to be 2 3. If one is unable to fire and unable to turn off and 3 is on, then automatically commutation failure will be takes place. Then 1 to 3 is going to be conducted. If 1 to 3 is conducting, automatically will get as a drop, because the A phase and B phase average only are coming in the load side. So some amount is going to be dropped, let it be as a minus omega less by pi into ID, that is 3 phase 3 omega less by pi d into ID. So like that you will get it as a some of the problems if commutation failure. That is the reason we need to prevention of commutation failure of the inverter. So these are the some of the desired features of a controller. Still some more will see that there is a prevention of arc back of the rectifier walls. So this is one of the fault, arc through, arc back, all these things. So it will come under the next unit. Anyhow, so this is also we need to prevent in the rectifier station. In a multi-anode walls, because walls are not only one wall, it may have the different configurations. That is the choice of configuration we observed in the first unit. Based on that, we will get it as a multi-anode walls also, providing as a sufficient anode voltage before ignition occur. So that we can notice in case of power electronics also, one of the factor is there in the parallel operation of SCRs. There is a below finger voltages. So what is that concept is when all the devices are operating in parallel, suppose one of the device is turn on time is more than others, then what will happen? Other devices will conduct some 10 devices are in parallel. First device turn on time is more than the rest of the devices. Let assume that n minus 1 devices turn on time is some 2 milliseconds of time, and first one is 3 milliseconds of time, just for example. And what will happen when the pulse is given to the string, then second, third, fourth and so on, the walls are on. And if that are all walls are in parallel, if other walls are is conducting, then automatically voltage across that will be as a minimum, very minimum. It is only 1 to 2 volts. Then that voltage is appear across the wall 1, but at third milliseconds of time the device will not be turned on, because that 1 or 2 volts is very less voltage. It is below the finger voltage, and hence that particular device will not be turned on. So only instead of 10 devices, only 9 devices will carry the load. Then again overload problem. All these things consequent will happen. So that is the reason here sufficient. If the voltage is less than that finger voltage, it will not trigger. No, that means sufficient voltage is required to fire the device or to forward bias. For that reason we mention here sufficient anode voltage, that is the above the finger voltage. If it is below the finger voltage, it will not be triggered. Keeping the voltage at the sending end of the line constant at its rated value, there is as possible in order to minimize the losses for a given power. So the loss has to be minimized. So voltage at the sending end of a line constant and at its rated value to minimize your power losses. Controlling the power delivered, or in some cases frequency at one end. So we need to control the power delivered to the system, or even control the frequency in the AC side. So that is the one of the desired feature. And then control system should not be sensitive to normal variations in a voltage. But if we are operating through control, anyhow we have as a control strategy, and if it is very sensitive with voltage variations, automatically there is a AC side is always fluctuating some small voltages. If I say, even for single phase, let us assume that if I say as a 220 volts, it may not be fixed exactly as a 220 volts. It may vary up to the 230 also. If that small variation also, if we are counting to the our control strategy, our controller is considering that scenario, that leads as a major problem. That's why control system should not be very sensitive in the normal variations in voltage. That is a very minute variations, you can consider it as a constant. So that is also one of the thing we need to consider. And control should be fast and reliable and easy to implement. This is also very important feature while you are designing that system. That is only the advantage of HVDC, other than that other controllers. So HVDC control system is very fast, right? Whether it is a alpha variation or a beta variation in the inverter side, alpha variation in the rectifier side, whatever it may be, it is a faster control action is going to be takes place. Not only the faster, it is also very reliable operation. The system will be very reliable, and it has to be easy to implement. And there should be continuous operating range of full rectification to full inversion. The control strategy now, like in case of firing angle, you can see that 0 to 180 degree alpha variation. So there is a full range of control is possible. We need to consider continuous operation of full rectification to the full inversion. That means the station 1, it has to be operate either a full rectification mode or full inversion mode of operation. That is the control range we can consider. Control should be such that it should require less reactive power. This also major problem if we are not constrained on this. If you are operating, the system is always required as a reactive power compensation. that is also additional burden. That's why while the system operation itself, they take care of the constraint, should not be as much the reactive power requirement. Should be required only less reactive power to adjust the voltage or to maintain voltage is a constant. Under steady state condition, wall should be fired symmetrically. So what is meaning of symmetrical configuration and asymmetrical configuration? This word come into the picture in case of semi converter configuration. The devices, two walls or two thyristors are connected in series in a same leg. Other will be in the only diodes in the other leg. Therefore, while you are operating the system, all the devices will not be operating symmetrically. Some device will be conducting more interval, some other device will conduct under less interval. So that is also, you can see that wall should be fired symmetrically. Control should be such that it must control the maximum current in a DC link and limit the fluctuations of the current. So current fluctuations has to be limited. Power should be controlled independently and smoothly, which can be done by controlling the current or voltage or both. So why these features are, after this class we need to see the combined characteristics of rectifier and inverter. So these are the desired features are required. What they're telling is here controlled independently, because the rectifier station and inverter stations are there. Both stations, they have their own control parameters. Like rectifier station is alpha and inverter station is beta or maybe gamma. Anyhow, gamma cannot be direct. If you are controlling the beta, in turn gamma also is going to be varies. So that is the reason controlled independently and smoothly, which can done by controlling the current way or by controlling current or by controlling the voltage or by controlling both. It has to be performed independently and smoothly. And control should be such that it can be used for protection of the line and the converter. That controller also we need to consider the protection of a transmission line and converter. In that equipment we have only two things, control stations and then transmission lines. So this controller also should be take care of that protection of a transmission line as well as the converter. If converter fails also, we have to shut down the system. So that is the thing. Control should be such that it can be used for the protection of line and the converter. And these are four reasons for keeping the power factor is high. So this is one statement I made in the earlier the desired features. So the power factor must be high. So why the power factor need to keep? There I mentioned as a statement, power factor must be as much as possible you have to keep it in the high. And why this we need to keep high? There is a four reasons. You can see the first two reasons converter itself consideration, and other two concern as AC systems. So AC is because of the AC side, the two reasons, and then controller itself as a two reasons that we'll see. First reason is to keep the rated power of the converter as high as possible for given current and voltage rating of a walls and transformers. So that means rated power of the converter as high as possible for the particular given voltage or and current in the transformer side. So that is the one reason. Another one is a reduce the stress on the walls and damping circuits. So damping circuit in the sense RC1, RC2. So reduce the stress on the walls. If voltage stresses are there in the wall or current stress are there in the walls, automatically there is a chance of failure of the wall. So what you have to do is you keep that power factor is high so that it will reduce the stresses on the wall. And third reason is to minimize the required current rating and the copper losses in a AC lines to the converter. So you can minimize the required current rating. Why? Because the power P is equal to V into I into cos phi if one of the factor is more, to get that same power, instead of zero point 0.8 power factor or a 1 power factor, you can see 0.8 power factor you may require more current with the constant voltage, let us assume that. And if we keep that instead of 0.8 to 1, then automatically current requirement will be less. So if that is happened, automatically losses also will be minimized. That is the third reason. And fourth reason why you have to keep that power factor is high, minimize the voltage drops at a AC terminals and converters in the loading increases. When the load increases automatically, AC side there is a problem will arise. So because some drop will be takes place. So that's why minimize the voltage drops if you are keeping that power factor is high. The power factor can be raised by adding shunt compensators. This is the remedy how we can able to increase the power factor. We just make use of the shunt capacitors. So that why that shunt capacitors and all, this logic is everybody known. Normally in a system, if you are operating with induction motor, let consider as a transmission line, you are tapping the power, AC power let it be, and you are operating as induction motor. Induction motor is a non-linear load. So what that will do, the motor is a in a transmission line, it absorbs the reactive power. If you are observing the reactive power, automatically voltage will be drops down. So if you are operating such loads, many number of loads in a transmission line, automatically voltage is going to be dropped down continuously, and then the end user, you won't get as a normal voltage or a rated voltage. Then what the people has to do, you have to compensate that. So what is the compensation is there? The reactive power will absorbed by the induction motor. So you keep as a capacitor or condenser, so that there itself how much reactive power is going to absorb, you can able to increase that reactive power supply through the capacitor. Capacitor will generate the reactive power, so that both reactive powers will get cancelled out. That is only the compensation of a constant voltage. So like that, in the earlier there is a one instruction in the agriculture lands, whatever they use as borewells, the induction motor, the department are insisted to place as a condensers near to the load side, so that the dispatch center is, there is no burden to compensate the reactive power. So individual load centers itself, in the particular load, you can able to what you call it as compensate that reactive power, so that it will be minimize the cost. So that is what there is a shunt capacitors you can use to compensate that. If this is done, then also be disadvantage because of the cost capacitors. So cost of the capacitors are more, no, once to compensate that we require as a capacitor. Once if we install the capacitor, automatically cost of that will be high. And switching them as the load on the converters varies. So that is not a fixed condenser, like um, uh, through switching action many number of condensers are there, and depends on our requirement of the reactive power, you can able to switch on the capacitor. So whether you can use that number of capacitors more or less, that decided by the load. And now we can see that there is a power factor of the converter formula. As you know that one relation in the previous, VD is equal to, that is the average output voltage, VD is equal to VD naught into cos phi. That is equal to, if you are considering overlap, final average expression of voltage, I can represent 1 by 2 cos alpha plus cos of alpha plus mu. This is the case of alpha and mu represent as a rectifier formula. And if we consider to the inverter, what will happen, instead of alpha replaced by the gamma, that we have noticed in the previous class. So now there is a cos gamma plus cos of gamma plus mu. This is the formula for power factor in the inverter side, and this is the rectifier side. And for the reasonably high power factor, so what is the constraint? This cos phi is a power factor. what I want to do, I have to keep this power factor is high. Alpha or a gamma. Alpha means in the rectifier station and gamma is in the inverter station. Should be made as small as possible. So then if I keep this alpha is small or gamma is small, then your power factor will increase. So that is what based on the equation. And in a rectifier this is easy, but whereas how it will be easy, you can, it is all our control of a rectifier station, and inverter also possible, but it is not directly you can control the gamma, you can control the beta there, and in turn gamma will varies. So that means for the rectifier station easy to control, because making alpha is 0, that is easy way, and like a diode rectifier it will operate. So our intention to keep our power factor is high, what we want to do is, they mention alpha or a gamma must be keep it in the minimum or as small as possible. So but on the rectifier station cos alpha is equal to 0 or alpha is equal to 0, cos 0 is equal to 1. So their power factor is equal to 1, like that. So cos alpha is equal to 1, you can make that, but in the inverter more difficult. So in inverter gamma variation is a more difficult because it is not a direct variation. In order to avoid commutation failure, so I told there is a voltage must be keep some minimum level to turn on the devices, otherwise there is a commutation failure will be takes place. So that is the sentence is here. In order to avoid commutation failure, commutation must be complete before the voltage is reversed at gamma is equal to 0. You cannot keep that gamma 0 directly, because what they mention here is before commutation the voltage means the voltage has to be reversed. So before that the commutation has to be takes place. Some margin angle, preferably that margin angle will be 15 degrees for 50 Hz supply and all. We cannot control gamma directly, but instead must control the ignition advance angle is a beta, because there is a relation between gamma and beta. Beta is equal to gamma plus u or a mu. Then you, once if you are controlling the beta, automatically gamma also going to control gamma is equal to beta minus u or a mu, in accordance with the value of overlap. So based on the overlap interval, you just control your beta, automatically gamma also going to be controlled. Any of the prevailing direct current and commutating voltages. So you can able to control the beta and you can able to control the alpha to keep your power factor is high. So to keep power factor is high, we need to make it alpha is 0, one aspect, and beta also keep it 0, but that should be take care of the problem. But directly beta cannot be controlled, only through gamma has to control. And that is the case of because of some inaccuracy in the commutation of beta and possibility of change in the direct current and alternating voltage even after commutation has begun. So once the commutation also begin, so there is a, that's what for the reliable operation there is a margin angle we have to give it, that is a 15 degrees we have to wait, and then only we can proceed with the commutation process. Sufficient commutation margin above the minimum angle required for deionization of the walls. So that is what you have to ensure that the wall current must be completely 0, then only the process will be takes place for other set of the devices. That's what sufficient margin angle has to be given. And easy and safe way would be the choose a large value of beta. If you are keeping large value of beta, this way however lowers the power factor. So if you do that way, power factor will, but we can do the gamma, but if you do the beta some extent, because to improve the reliability operation, then what will happen, power factor will reduce and then rises the stress on the walls. That also one of the factor I told you why we need to keep that in the higher power factor. So wall stress will increase, power factor will decrease. So that will happen if I increase the beta. and better way is to compute the firing angle required to obtain the constant extinction angle. So what we notice from this analysis is what alpha variation is easy, but beta variation is a difficult. But if you do that way also, even through beta and to change the gamma and all, there is a complication is arising. That's why what they will do is you are keeping the gamma constant and try to adjust your alpha to maintain what you call it as power factor improvement. So under normal operations, rectifiers will take care of the current. These are the scenario. In the further all analysis will consider this. Rectifier case, constant current operation, and inverter will take care of the voltage. So that's what there is a something. You can see that CC operation, that is a rectifier, will consider constant current control operation, and inverter constant extension angle control. So that means CC control strategy is belongs to the rectifier, and CEA control strategy is belongs to the inverter side. And then let us examine how AC voltage changes reflect in a DC current. That means if AC voltage changes, whether it is in the inverter side or in the rectifier side, then what is the impact on the DC currents? Because there is a two stations now. If AC voltage is drop in the rectifier station or drop in the inverter station, similarly AC voltage is increase in the rectifier station or increase in the inverter station. If that is the case, what is the DC current? That we can see that. So in which controller has to exercise to make the DC link current as a rated value. So if the thing is happened in the inverter side or a rectifier side, you have to keep that DC current at a rated value. And the first scenario, you can see that one thing you must remember, rectifier will take care of the constant current, and then inverter will take care of the constant extension angle control. So first scenario, you can see that increase in the rectifier voltage. So if we are increasing the rectifier voltage, current in a DC link will also increase. To control the current in the rectifier end, controller will increase the delay angle. So why we need to increase the delay angle? To maintain rated current. So DC link current has to be rated value, but if in rectifier voltage increases, automatically DC link current also will increase. But to maintain constant, obviously current in the rectifier end you have to maintain constant. So controller will increase the delay angle, while at inverter and controller will maintain a constant extension angle. Now you can just analyze this. Voltage increases, automatically current increases, but I need to maintain current in the rated value. For that, what is the possible option? You can increase the delay angle alpha. If alpha increases, what will happen? Voltage automatically will decrease, because our formula is Vd is equal to Vd naught into cos alpha. Vd naught is a constant and cos alpha varies, then automatically our voltage is going to be decreases, and hence our link voltage current maintain constants. That is the point there. And increase in the delay angle was in the power factor. So that is also the problem. So what is the problem is here, if these are the cases may arise in the system operation, then what is the consequences I am explaining. Increasing the rectifier voltage, current will increase, and hence we need to maintain constant. You decrease the alpha. Once alpha decreases, the other side, inverter side is maintain constant CEA, that is a constant extension angle you can maintain constant. And now increase in the delay angle, we are increasing the alpha to maintain constant current, so that what will happen, as I mentioned there, alpha must be keep it 0 to maintain a higher power factor, but if we are increasing the alpha, automatically power factor will be decreases. Generally it is a control in steps, therefore tap changing is done. Normally This all will not be in the rapid change, so it will be in the steps fashion. You can do rest of the portion once if you change the alpha, and rest controller will take care of the tap changes. And increase in the inverter voltage. First thing is increase in the rectifier voltage, that is other side. And now what we have to do is increase in the inverter side voltage. Then current in a DC link will decreases, because inverter side voltage is increases, and this side current in a DC link will decrease to control the current in the rectifier. Controller will decrease the delay angle, because this is going to be decreases the alpha. Why we are decreasing alpha, then why increasing alpha there, and why we are decreasing alpha here? Because to decrease the current, to maintain constant, again you have to boost up. So for that reason you have to keep that alpha must be minimum, so that voltage will be rises and maintain the current constant. And again the inverter side you will maintain constant extension angle. So these are the two scenarios. And as the same logic, decrease in the delay angle, improve the power factor. So if you do this way, power factor will decreases, and if you do this way, second way, means inverter voltage increases and you are decreasing the alpha, alpha decreases or goes towards the zero, automatically power factor will get it as unity side. That is the reason this sentence will be decreasing the delay angle, improve the power factor. Generally it is the controlled in steps, that after again same thing, it all this last point is common, so the variation is in the steps. So next part will be the taps will be um, changes. First we can do this alpha side and then tap changes. And third one you can see that decrease in the rectifier voltage. So previous two things are one thing is increasing the rectifier side and then increasing the inverter voltages, and other versions decrease in the rectifier, again decrease in the inverters. So decrease in the rectifier voltage, currents in the DC link will decrease to control the current in the rectifier. So that will decrease the delay angle. Once decrease the delay angle, you can increase the power factor. So decrease in the delay angle automatically improve the power factor. And other version, if the further decrease in the rectifier voltage characteristics falls below and constant extension angle characteristics does not intersect the, that characteristics will sweep, both has to be coordinate. And if the keep on decreasing that alpha, this rectifier characteristics will not be intersect with the inverter characteristics, so that you don't get it what is the operating point of a voltage and current. So that is also the problem. We'll see that. Another one is a decrease in the inverter voltage. The third one is a decrease in the rectifier voltage, and fourth one is a decrease in the inverter voltage. Current in a DC link will increase. So once the current increases, you know the logic is increasing the delay angle, so that the voltage will be decreased and then current will maintain constant. So that will be the thing we need to do. So obviously increase the delay angle, again power factor will be worse. So that is the problem. Now we'll see some of the ideal characteristics, then move on to practical characteristics. So what is the ideal characteristic? You can see that rectifier will take care of the current, that as the statement has already proved in the previous slides, so that the line parallel to y-axis. So if it is a current, what we can represent in the VI characteristics, we can mention this is a current line. So that is a line parallel to the y-axis. As inverter equation will gamma is negative slope. So we can see the alpha and gamma cases for the inverter as well as the rectifier. Alpha is the rectifier, gamma is an inverter. The point where the rectifier current control and inverter voltage control coincide, they're exact in the operating point. So if there is a something slope on this side, then you can make use of this is the point. So this is the point of operating, like that. So that is the ideal characteristics. Rectifier characteristics can be shifted horizontally. So that means you can move the rectifier characteristics by decreasing the voltages and all. You can able to move like this, and still you can get like this. Then the operating point is going to be changed. If your operating current is maintained constant, and we are decreasing this way, and you can get it as a current horizontally. You can adjust the current command, and if the measured current is less than the command, that means required, there is a regulator advance the firing angle by the decreasing the alpha. So the inverter characteristic can be rise or lower by means of a transformer tap changes. So because the inverter side rectifier side initially will be do alpha and then gamma, but later there is a tap changes only. When the tap is moved, the constant extension angle regulator quickly restore the desired gamma, and we are changing the tap such a way that the gamma must be keep it in the desired value with a faster rate. As a result, DC current change with the quickly restore the current regulation of the rectifier. So if anything is happened, you have to restore the system by changing the control rapid. Now this is our characteristics as I mentioned. There is a rectifier, constant current, there is a CC, and then inverter. So whatever I shown here, these are ideal, but practically it should not be as a like straight line fashion here, or like straight line here. So there is a slopes will be there in this side, and this also will be slight slopes will be there. Then the later in the actual characteristics will differ on this, but it is the point where AB is the rectifier at constant current, and then CD is the inverter at constant extension angle controller, and by intersecting these 2 points at point E, that is our operating point. From this operating point, you can able to get E point. This is the current and this is the voltage it is going to be operated. So this is the ideal characteristics of this, and later we will see the actual characteristics and then combined characteristics of a rectifier and inverter. So that we'll see in the next class. Okay, you can give the attendance and leave. How many of you? 27 are present.